Okay, let's get started. Here we go. Let's get started. Ready? Okay, so make sure if you haven't passed the mastery test, you get into either Morgan or my or Cerny's office hours to take that before Thanksgiving. Got to pass it. Everyone's got to pass the mastery test. In terms of the web work, there were a couple problems that had some things that we hadn't talked about yet. I realized that. And so those are extra credit. Okay? So if you got those, extra credit. So things that talked about, especially inflection points. We never talked about inflection points. So those will be considered extra credit. So if you got, I think, all but 3 of them correct, then that's about like full credit, okay, on that assignment. Okay, so let's press on here. The goal is to do top hat at the end of class. Okay, top hat at the end of class. Okay, so this is the main idea. When we're coordinating functions and their derivatives, this is the main idea. It's like 80 or 90% of what you have to know to apply to make sense of these problems. And we say that if the function's output y is increasing, what do we know about the rate of change? All right, so this is huge. This is huge, right? So if a function's increasing, its rate of change is positive. So let's just quickly kind of justify that. So we're going to justify that using the fact that rate of change is calculated by k equals delta y over delta x. Or dy dx, we should say, actually. So we're going to start with the fact that the function's output y is increasing. So we'll start here and use k equals dy dx to kind of reason through why that rate of change would have to be positive. Take a minute, see if you can come up with it, right? So it's like a 3-step proof. It's like a 3-step proof. If the output is increasing and you know that k equals dy dx, why does k have to be positive? Talk it through with the person next to you. Why do I mess with it? There we go. Okay, you just come up with something like this. If y is increasing, then the final y is greater than the initial y, right? And if that's true, then what about dy? Greater than 0. Okay, if the final y is greater than the initial y, then our dy is greater than 0, and this was always under the assumption that x was increasing too, right? So therefore that k value has to be positive, right? So it should make perfect sense. Okay, and then what about if the function's output y is decreasing? Rate of change is negative. Negative, and how would we prove it? Tell the person next to you. Go. Given that the output is decreasing, why is k negative? If y is decreasing, then what does it mean for? What does it mean? So what's the first conclusion you can make if y is decreasing? You've got a starting y and an ending y, and y is decreasing. What does it mean? Y initial is greater than y final. So what about dy? Less than 0, right? Less than 0. Okay, so if y is decreasing, then your final y is less than your initial y, and therefore if you were to find the change in y, it would be negative. All the while k is dx is positive, so then that k is negative. Okay, so there's not much to think about to see how this is true, right? There's not much to think about. If it's decreasing, then your final y minus your initial y has to be negative, and then that will make our k negative. Or m, we were calling it m, right? So we called it m. I'm going to update the slide, okay? All right, so that's the major point. If values of the derivative are positive, values of the function are increasing. And if values of the derivative are negative, values of the function are decreasing. Okay, and then we emphasized last time, just to remind you, that these principles hold true for any function and its derivative. So it holds true for accumulation or an amount function and its derivative, its rate of change function. But then all these same principles apply to what also? Yeah, what if your original function was a rate function? And then its rate of change function is what we call the second derivative. So these same principles apply to this relationship of functions. Okay, why? Because this is simply the rate of change of this, or this is the derivative of this. And if it's the derivative, then all those same principles apply. Okay, and then so there's one additional idea that kind of gives us almost like 99% of what we need to reason about these problems, and that is when the second derivative is positive. So what would that mean? If the second derivative is positive, that would mean that the first derivative is increasing. And so then what is f doing if the first derivative is increasing? So we think about increasing. So you see that as this U or this cup shape unfolds, that's always an increasing rate, right? Increasing rate, bending upward, whether it's going down or up, doesn't matter. It's bending up the whole way, okay? And so that's an increasing rate of change, getting less negative or more positive. And so in that case, if your rate of change is increasing, then we know that the second derivative is positive. Again, back to the original principles. So then we can say that when the second derivative is positive, the function is concave up or turns counterclockwise. But really key that when you look at that and you see it from left to right, you see, oh, the rate is increasing all the way through here. The rate is increasing, getting less negative and then more positive. Okay, and then similarly, what about when the second derivative is less than 0? Then we know that means the first derivative decreases, back to our core principle. And if the first derivative is decreasing, then it means it's getting less positive or more negative. So across this whole part of the graph here, what do we have? We have a decreasing rate of change, and therefore a negative second derivative. Okay, any questions? So those are the basics, right? And so we have all these different problems. We're coming at these ideas in all different directions and with different applications. But it goes back to having being really confident with these basic principles. And having technology that works. Okay. All right, so let's talk about what's called critical values and optimization. A critical value of a function f is any value of x. So first of all, a critical value is the value of the independent variable. Okay, it's the value of your independent variable where the value of the function exists. There's a valid output. There's a valid value to the function. Okay, that's the first criteria. And then the second thing is if the first derivative is 0 or the first derivative does not exist. So when both these criteria are met, you have what's called a critical point at that x value. Or sorry, the x value is a critical value. Critical value. So you have the function value has to exist, and the first derivative has to be 0 or not exist. Okay? So if 0, so we're looking at this first case of number 2, if 0, then what happens? The rate of, what we're saying the rate of change is 0. So the function, the accumulation, if the rate of change is 0, we can conclude that it stops or pauses momentarily, increasing or decreasing. Right? So if the rate of change is 0, then the accumulation is holding steady for a moment, or maybe for more than a moment. But at least at C, at the moment of C, accumulation is holding steady right there at that moment. Why? Because the rate of change is 0, and the function is not accumulating any quantity, right? It's holding steady. So there's different situations we have for this case, all right? So we're going to kind of investigate all the different ways that we could be accumulating along, and then all of a sudden your accumulation pauses, or the first derivative is 0. So let's take a look at these. Okay, and the first one is what we call a local max. A local max. Okay, so over here on the right, I'm showing the accumulation function. And we have a high point, right? We have a local max. And so we want to kind of think of this, we want to see this dynamically, okay? There's kind of 3 parts to, well, let's first let me just, before we get to that, take a look at, I want you to first look at the black arrow here on the x-axis, which is representing the independent variable increasing. Okay, so watch that for a second. Okay, it's really boring, right? Okay, so what's happening with the independent variable? How are we framing this? How are we framing this with the independent variable? Yeah, so we're just looking at a constant increase, right? So we want to focus on the dependent variable. So in order to do that, we want to keep that independent variable steady, increasing steadily. So now we want to look at the pink arrow. The pink arrow is showing us the story of a local max. The pink arrow is showing us what the story is of a local max for increasing x. Okay, and there's 3 parts to the story. What's the first part of the story here for a local max when you're looking at that pink arrow? What's the first part of the story? It's going up, right? It's going up. So to the left of a local max, increasing, right? It's increasing. You should see that. Okay? Then what's the second part of the story? What happens to that? What's happening to that value of our dependent variable next, right? Now. Pause, right? Look, watch. Pause. You see that? Watch it again. Ready? Increasing until a pause. That's what happens at the local max. The value of the accumulated value, or the whatever amount we're looking at, pauses for a moment. And then the last part of the story is right now. So what's happening? Decrease, okay? So the accumulation is increasing, and then there's a momentary pause, and then decreasing. And when you have that story, what you have is a local max at the pause. You have a local max at the pause. Okay? So now, based on our fundamental principles about coordinating a derivative and function, you're going to take this now, and we're going to apply it to the derivative, okay? The rate of change function for f. It's increasing, and then it pauses for a moment, and then it's decreasing. Can you sketch what the rate of change function will look like for that progression of the accumulation function? Give it a try, okay? Oh, okay, forgot. All right, so what will the rate of change function look like? It goes back to our core ideas about this, right? Accumulation functions increasing means what for the rate of change? If the accumulation is increasing, everyone should say it. The rate of change is positive. If the accumulation pauses, the rate of change is 0. If the accumulation is decreasing, the rate of change is negative. Okay, so let's put the pause in there. So where should the rate be here at C? At 0, right? And then over here before C, x less than C, you told me the rate of change should be positive. Up here, right? Up here somewhere. And then to the right of C, where the function's decreasing, negative. So what will the graph of the rate look like around a local max? This. I'm being squiggly just so it's just general, okay? This should make sense. This just goes back to those initial principles we said. If a function increases, rate of change is positive. That means it's above the x-axis. The rate of change is, if the function is decreasing, rate of change is negative, below. Okay? So then what about the second derivative? So what's happening here with the first derivative, and what can then we can conclude about the second derivative? Talk for a moment. What do you think? Just use the fundamental principles. Just use the fundamental principles. If a function is increasing, its rate is positive. If a function is decreasing, its rate is negative. Just use that to figure out what the second derivative will be like. So what do we think? What's happening to the rate there? What's the rate doing the whole way? Decreasing. Therefore, the derivative of that would be negative. So the graph would be where? Right, down here. Like this. It's the same principle again. We see the rate must, from what we concluded, the rate must be decreasing. If a function is decreasing, then its rate is negative. Okay? And then finally, let's just check it. If the second derivative is negative, what does it mean for the original function? Yeah, it means that the rate of change is always decreasing, making a concave down shape, and it matches, right? So second derivative is negative means concave down. This is what characterizes a local max. All this stuff, okay? The function increases, pauses, decreases. The rate of change is decreasing, and at the pause, the rate of change is 0, and the second derivative is negative. Does it make sense? Okay, so now you do it for local min. Yeah. Okay. I don't have a fancy animation for local min, but you can do it. So you're going to start here. Tell the story of the accumulation, conclude what about the rate, and then further conclude what about the rate of the rate, or the second derivative. Go. Okay, what's the story of the accumulation? 3-part story, right? 3-act play. What is it? Decrease. Pause. Increase. Okay, so at C, what's the rate of change? 0. So what's this graph of the rate going to look like? If the function is decreasing, the rate is? So, what does that mean for this? It's down here. It's down here, right? It's below the x-axis because it's negative, right? And then? goes through 0, and then the function values are increasing, therefore rate of change is got to be up here, positive. So what it'll look like? That. Okay, and then we want to continue on and talk about the second derivative. What can you say about the second derivative based on this rate function that this little piece of the rate function that we came up with? Why positive? Rate of change is increasing. And whenever a function increases, its derivative does what? Is what? Positive. And if the second derivative is positive, what does it mean for the original function? And that's what we got. Concave up, right? So this means positive second derivative means increasing first derivative means turning up, right? Turning counterclockwise or concave up. All right. Super important slide right here so when we get to all these really hard optimization problems, and they're about trig and economics and physics, and they're all different. You have to have this down. So if you have this down, it's really going to help you analyzing those situations. Okay, so if the rate of change is 0, is a max or min guaranteed? Is that what you always have? When you have the rate of change equal to 0, we've seen that the rate of change of 0 is at a local max. The rate of change is 0 at a local min. So if you start by saying that the rate of change is 0, does it have to be a max or a min? So can we think of something else that could happen? Okay, so, all right, that's true. But so what we have is another situation is called a rest stop. Okay, so you're driving down the highway, right? And you really got to go. So you pull off, and you go. And then when you get back on the highway, do you turn around and go the other way? No, what do? So on these rest stops on the highway, you can only keep going the same way you were going, right? So what happens here? We've got increasing, and then a pause. We all have to pause once in a while, right? And then increasing again. So you see how at x equals c, what's the value of the derivative? It's 0 because the accumulation for that, at the moment x equals c, the accumulation is not increasing or decreasing. It's pausing. But we don't have a local max or local min. Okay, so I want you to draw what in the vicinity of, or right around the moment x equals c, what will the rate function look like? Go. Right around x equals c, what will the rate function look like? Everyone draw it. And then I want you to draw the second derivative based on the first derivative. Draw the second derivative based on the first derivative. Okay, here we go. So, increasing, pause, increasing. What does it mean for the rate? Positive, 0, positive. So what will that look like? The rate's going to be positive, and then it's going to be 0 at that moment, and then return to being positive. What will it look like? Yeah, so it's going to have to come down and just touch for a moment, and then go back up like this. So we're just talking about these little graphs are just for a moment around C, okay? So don't think of this as, even like it's not even a width of 1. So just think of this as we're just talking about at the moment of the critical values, okay? So now, we've got this graph here, and how can we deduce what the second derivative is based on what we're looking at here? So what do we focus on here? The rate is doing what? Decreasing, therefore? Negative, good. And then the rate is increasing. So its derivative would be positive. So the rate is decreasing. Its derivative then is negative. And then look, the rate pauses, right? The rate is pausing, as well as the function, right? So here the accumulation pauses, but also the rate pauses. You see that? If the rate pauses, then the second derivative is 0. And then rate increases, therefore second derivative. All right, that doesn't have to be a line. So that doesn't have to be a line. Don't think it's linear, but it's just that idea that it's negative and then positive, okay? So what do we have when the second derivative is 0? Well, that means that the first derivative pauses, or the rate stops changing for a moment. Okay? The rate stops changing for a moment. And so what does that look like in the accumulation? That's what we call an inflection point. So again, let's review it. The second derivative is 0. Okay, if you're talking about the math, that's great. Just whisper, please. Just whisper. If the second derivative is 0, that means our first derivative does what? Pauses, right? Whenever a function's derivative is 0, that means that function is pausing. All right? So the rate pauses for a moment. If the rate pauses for a moment, then it's kind of like the rate stops changing for a moment. And so in this case, it's like the rate is slowing down and it stops changing, and then the rate starts increasing. So the rate was decreasing, and then the rate pauses, and then the rate starts increasing. So when you have a pause in the rate, you get an inflection point, and that's where it will change concavity. So in this case, it changes from concave down to concave up. Okay, so rest stop type 2. I want you to analyze the whole thing. Start by writing the story of the accumulation function, deducing what the rate function would be like, and then deducing what the second derivative would be like from the rate function, from the first derivative. Go. Draw the pictures. Draw the pictures. Okay, what's the story of the accumulation? First it's decreasing, then pause, then decrease. That's a type 2 rest stop. Rate of change. So rate of change, tell me. Negative, 0, negative. Negative, 0, negative. So at this type of rest stop, your first derivative will look like that. And now tell me about So what does that mean? It means increasing, pause, decreasing. So its derivative will be positive, 0, negative. Also an inflection point. Now this one changes concavity from concave up to concave down. Okay? Concave up to concave down. So not only, so rest stops are where both the accumulation and the rate pause. They don't have to both pause. One could pause or the other could pause. But in a rest stop, the accumulation pauses, meaning it stops going down for a moment, but then also the rate pauses. So the rate is what? Here the rate is increasing, right? And then it pauses, and then the rate starts decreasing. Okay? Rate here is increasing, getting less negative. Rate pauses, rate gets more negative. So with a rest stop at that critical value, both the accumulation and the rate of change pause. But in other situations, you can have one or the other pausing, right? Okay. Doesn't have to be both. Okay, so it all makes sense at the moment. But, you know, if there's all these other things swirling around in the problem that you're doing, do you have a firm grasp of this? Don't forget it. Do what it takes to learn this. Okay, so then we said the other way that you could have a critical value is if the first derivative does not exist. And I think we saw this earlier in the course, in the text. So the first one is a corner point. Did we see those? So we're going along here, and then all of a sudden, at x equals c, the rate abruptly changes. Not in a moment, but at an instant, right? So at the value c, the rate of change abruptly changes. So then you can't say what the rate of change is. Is it positive 3 like this? Or is it negative 1/2? Right? It doesn't exist. So at c, right there, the function exists. We have a y value. This is f. So we have a value for the function. That exists. But the rate of change does not. Because it's like, while we're staying at c, we have to do this like 90-degree turn, right? So what is our rate of change when we're doing this 90-degree turn? Who knows? It doesn't exist. Okay? The other way is if it's momentarily vertical. This is hard to draw, but I'll do my best here. So you're coming along like this, and then for a moment it heads vertical, and then, the best one I've drawn all year. Okay? So for one moment right there, the graph turns vertical. And so, similarly, the rate of change of c does not exist. This is a function, right? So there's only one value of the function at c. It's just that it's not that it stays. It's not that it stays at c, right? So there's still only one value of the function at c, so it exists. It's just that at that moment, the rate of change is infinitely great, right? So it's like the rate of change is undefined, right? So that's not what I should have written. Does not exist. And that's for both of these, right? So there's a corner point or momentarily vertical. Your first derivative will not exist. So these also are critical points. These are also types of critical points. Okay, so here is an example. We have this accumulation function, g, and we want to figure out the first derivative and the second derivative and get some values and make some conclusions. Okay, so first derivative should be easy, right? Super easy. 4x cubed minus 18x squared plus 24x minus 8, okay? So now, what is the second derivative? What is the second derivative? Well, it's just a derivative. It's still a derivative. So it's all the same rules, but it's just applied to the first derivative. So it will be, everyone, 12x squared minus 36x is 24. Okay, so second derivative is nothing more than applying all the same derivative rules to a first derivative and finding the derivative of that function. So now for these x values, we're going to plug all these x values in. So all three of these functions. So at 0, 0.5, 1.5, I want to get the value of g, the value of g prime, and the value of g double prime. And I'll just do it for you. There you go. So here they are. And so now based on these values, we want to make conclusions about what would g be like near that value of x, based on all the stuff we're learning. So near x, so for instance, third line, near x equals 1.5, could you sketch what the graph looks like for that moment around x equals 1.5? So why don't you take 5 minutes and see how many of these you can do confidently, okay? Go. So we're sketching what g is like right in that momentary, right around that moment of whatever that x value is, using the values of the first and second derivative. So you're making little sketches of g. For each x value, you're making a little sketch of what g is like right there around that x value. So somehow it's going to be going down. Now we're going to include the information on the second derivative. What does it mean to the second derivative? What's the function? G double prime is positive. What is the So if the second derivative is positive, it's your just the derivative is positive, it means that the derivative is positive. What is increasing? The second derivative is positive. What is increasing strength? Okay, first one. What does this tell us about g? No, g is the rate, the derivative is negative, therefore g is decreasing. Fundamental principle, right? Fundamental principle. Okay, so somehow it's going down. It's going to go down somehow. But now the second derivative is positive. So that tells us what?
It's decreasing at a slower rate. It's negative, but
It tells us that the first derivative is increasing. Increasing, right? So how can the values of g decrease and the value of the derivative or the rate increase? It has to do this. It has to do that because the rate, we're going down. -8 tells us it's going down. 24 tells us that the rate is increasing. So the rate is negative but increasing. It must be getting less negative. That's how rates increase, by getting one way, by getting less negative. Do you see it? Okay, this one. What's happening to the actual function g? It's not 0. This is the derivative. Look, it's 1.3. It's 1.3. The rate of g is 0, which means pause. It means it's pausing at 1.3. And also, the second derivative positive means that the rate is increasing. Positive second derivative means first derivative is increasing. So we have a pause with an increasing rate. What is it? What is that? We did it about 20 minutes ago. We have an increasing rate with a pause in the accumulation right there. What is it? Local minimum. Local minimum. Function pauses while the rate is increasing. Function pauses while the rate is increasing. That's a local min. Okay, this one. What's happening? G is, the first derivative is positive, then G is increasing. Second derivative is negative, means the rate of change is decreasing. So we've increasing, and the rate of change is decreasing. Draw it with your finger. Increasing, and the rate is decreasing. Looks like this. Okay, what about this one? What's happening to G? Increasing. This is positive, so G is increasing. And what is this telling us about the rate? The rate is pausing. So increasing, and then for a moment the rate pauses, and then it's going to go the other way. So this is an inflection point. An inflection point where the function is increasing. Not very pronounced. Right there. The rate positive tells us we're going up. The fact that the second derivative is 0 tells us that the rate pauses. So the rate was increasing, and then it paused, and now the rate's decreasing. So right there at that moment is where is what's happening at x equals 1. Okay, this one. Function is increasing. Rate of change is increasing. Draw with your finger. Increasing function, increasing rate of change. Just like that. Okay, last one. Many cases. There's lots of ways that both could be 0. We saw rest stops was one way that they were both 0. So rest stop is one possible way this could happen. But there's actually other possibilities, okay? Other possibilities. So just knowing that both derivatives are 0 is still inconclusive, okay? Inconclusive. Any questions on any of these? It all goes back to this fact. If a function is increasing, its rate of change is positive. If a function is decreasing, its rate of change is negative. We're just repeating that over and over and over again and then putting it together to draw these sketches.